Now we will discuss about axisymmetric problems. We will discuss about axisymmetric problems. In the third module of your syllabus, there is a section on axisymmetric problems. The problems of interest in your syllabus are thick cylinder, interference fit, and rotating disc. So, what is an axisymmetric problem? From the name itself, we will know that we'll get that we'll deal with the problems which is symmetric about an axis. Consider this cylinder here. This cylinder is symmetric about this axis, or we can get this cylinder if we rotate this rectangle around this axis. So it is symmetric about this axis. So it is an axisymmetric geometry. Axisymmetric geometry. And in such an axisymmetric geometry, if we take a cross section, it will be a circle. So if we take a cross section, then if the loading is also symmetric about this axis, it is uniformly distributed around this surface. If it is symmetric about this axis, then so here it is axisymmetric geometry and axisymmetric loading. Now this will give axisymmetric problem. A number of practical problems involves such solids of revolution. For example, we will have solid cylinders like this in engineering applications, or we will have hollow cylinders, and we will have hollow or solid shafts. We will have frustums and discs. Such shapes will be there. So this is an very important class of solid mechanics problems. So a problem to be axisymmetric, the loading and geometry both should be symmetric about an axis. If we have this body but loading is not symmetric about this axis, not symmetric about same axis, so the problem is not axisymmetric. So this is the condition for axisymmetric problem. One more condition is that the body should be isotropic and homogeneous. It is about the material of the body. Now we will try to obtain the governing equations for axisymmetric problems. What are the governing equations for a solid mechanics problem? We know that the governing equations are equilibrium equations and strain, displacement relations, and stress strain relations. And we have to obtain these equations to solve a solid mechanics problems. Basically, solving a solid mechanics problem is solving these differential equations, these partial differential equations, to obtain stress, strain and displacement. That are the unknowns. We have compatibility equations, that is also considered as the governing equations, and we'll have boundary conditions for solving the specific problem. So in this problem, since we have an axis of symmetry, so it is a body of revolution, solids of revolution. We are considering solids of revolution. For this case, we will use cylindrical coordinates. It is obvious that for solids of revolution we have to, it is easy to use cylindrical coordinates. Now the coordinates are, what are the coordinates? R, theta and z. Usually the z axis is taken as the axis of symmetry. So we align z axis with the axis of symmetry. Now we have theta and r axis. Theta and r axis. As the body and loading conditions are symmetric about z axis, we can say that the deformation is independent of theta. It does not vary with theta. So the deformation, that is, say, let us say u, deformation u is independent of theta. Now we can say one more thing. Since due to the symmetry, we can also say that the stresses and strains, the displacement is independent of theta, the stresses and strains also, if stress tau is independent of theta, any stress component tau ij is independent of theta, that means it does not vary with theta, and any strain component epsilon ij is independent of theta. Now we can obtain the first set of governing equations, that is the strain displacement relations. We will start from general 3D strain displacement relations in cylindrical coordinates. Okay, what are the general strain displacement equations for cylindrical coordinate system? That is, these are the general equations, strain displacement equations for cylindrical coordinate system. Now here we know that for an axisymmetric problem, everything, stresses, strains and displacement, everything are independent of theta. So every term which shows dou by dou theta, every dou by dou theta term will be 0, will go to 0. So displacement, as every displacement is independent of theta, these terms will be 0. One more thing I forgot to say is that for axisymmetric problems, generally we assume u theta is equal to 0. So what will happen here? This equation also will be 0. This will be also 0, 0 by r, that is it. So gamma r theta will be 0, and similarly this will also be 0. Gamma theta z is equal to 0, and here these terms will be there. Okay, these will be the equations we get for strain displacement relations we get for axisymmetric problems. So we got a simplified set of equations. Actually this is the main aim of considering a problem as axisymmetric problem, because we can simplify the calculations. Now we will check the next set of governing equations, that is stress strain relations. So these will be the stress strain relations for axisymmetric problems. Here we have only 4 strain components. What happened to other 2 strain components? We know that gamma, theta z and gamma r theta both are 0 from the strain displacement relations that in the previous slide. Also say that for an isotropic material, tau theta z and tau r theta both will be 0. So we can find the stresses in terms of strains like this. The next set of governing equations are equilibrium equations. So we will find out the equilibrium equations for axisymmetric problems. Okay, we will start from the general equilibrium equations for polar coordinates in r, theta and z directions. Okay, we will start with r direction. In r direction, the equation will be, these are the general equations of equilibrium, 3-dimensional equations of equilibrium in cylindrical coordinates. So here this term will be 0, since it is any stress component will be independent of theta, so this term will be 0. And for now we consider the equation in z direction. Now we have here similarly this term will be 0. Similarly for theta direction, we have tau r theta is equal to 0. Since tau r theta is 0, we have this term is 0, and since tau theta z is 0, this term is 0, and since sigma theta is independent of theta, so this term will be 0, tau r theta is 0, and obviously b theta will be 0, so this equation vanishes. So now for axisymmetric problem, the equilibrium equations reduces to these 2 equations. Here these 3 times will be there, and here this time 3 times will be there, and body force components will also be there. So for an axisymmetric problem, the equations can be, the governing equations will be this. So how many governing equations are there? 1, 2, 3, 4, 5, these terms will be 0, 5, 6, 7, 8, 9, 10. Only 10 equations with 10 unknowns are there. So in a general problem, general 3-dimensional problem has 15 equations and 15 unknown. So whether we are using computational methods or exact methods, the complexity of the problem is reduced when axisymmetric assumptions are made.